Like,
It's not like Wisconsin.
No.
Good to see you.
How was it?
it was okay. I thankfully wasn't ever that sick. It was mostly just really lonely.
Yeah, normally it's that.
It was hard to be alone for
Like
that long.
20s.
And like there's just nothing to like tie me down in the middle of the night. Nothing to do ever except
Like a January issue.
Yeah, but that's like how winter.
yeah, watching TV.
I
I had a lot of before getting it down. Maybe no one too seriously, but it is, it's going around.
All right. So, last time we started talking about making molecular orbital diagrams. There's a couple of rules we went through. Sigma is more important than pi, which is more important than delta. And this is an overlap sort of estimate, right? Sigma overlap is greater than pi overlap, which is greater than delta. You can't delete orbitals willy-nilly. So if you put in 10 starting, you should have 10 product molecular orbitals when you combine them. The energy difference between the orbitals dictates the strength of their interaction. This is approximately true. And you have to position the orbitals on the diagram in a way that makes sense, okay? So we typically begin with atomic orbitals, and the relative ionization energies of those orbitals are shown on the diagram for the atomic starting state. And when you combine them, it makes it easier to obtain a molecular orbital that makes sense. And this is partly because the energy of the MO and its proximity to the AO, the starting orbital, tells you something about the character of the molecular orbital you've made, right? So you have a C and an H making a bond, and they're split like this. When you make the MOs, then you know the bonding orbital is like the hydrogens, and the anti-bonding orbital is like the carbons. There's like a charge transfer that happens. And so anyway, position the starting orbitals correctly. So let's do another example today. And this one is a little bit harder to see. The group theory really is helpful. So we're going to start off with methane. What's the point group of methane? PE. Start off by carefully drawing a 3D box. And then try and find the center of mass of this box, your carbon. We're going to position some hydrogens here. Here. Here's our methane. The middle of our box. Okay, so there's a couple of operations here. We have our C3 along this CH bond, swapping all three of those hydrogens. There's A. C2 axis here swaps these two hydrogens, these two. And of course, the C3s could be along any CH, and the C2s could be on any face. What's another operation for TD? There's no inversion symmetry. S4. you know, if you took this thing and sent it to the other side, there's no hydrogen there. S4 is a good answer. You can take this axis here, rotate this position to that position and reflect. Anything else? Simpler one. Sigma D. Sigma D is where?
Sigma D is between the, like, the hydrogens, but sigma D would be like across the top.
Yeah, so I would just say that there's a planar reflection from here that reflects these two hydrogens and contains these two. Okay, you can move those planes around. You can either reflect those two, or these two, or these two, or those two, depending upon where you put them. So let's draw one here. There's a plane right there. A little messy looking. Sigma D. All right. So I'm going to draw out the character table for TD in a minute. But before I do that, we're going to pick our XYZ coordinate system this way.
Can I ask something about the sigma D?
Yeah.
So it's going through like the different C2 axes that are, it's cutting in between them. So you have one that's going, the C2 rotations are going through each face of the block there of the cube.
Yeah, so like each face has a C2, right? So you can see how this plane kind of slices this face in half, and in fact, there's a C2 operation coincident with that plane. Okay, so I'm going to choose my XYZ coordinate system this way. And, you know, that's a little bit unconventional. Why is that? Normally we put Z along the principal axis, okay? And this is the principal axis, the C3.
Is it because it has such high symmetry that any axis can be principal?
I guess so. It's kind of hard to think about X and Y and Z unless they're lined up with the cube that we've drawn here. The cube kind of is a easily conceived reference. Symmetry, if you put Z along here, then X and Y don't really line up with any of the CHs, and you'll see it makes life easier in a minute. Yeah.
But here, we don't really have a true principal axis, right? Because there's four.
That's true. Yeah. This is the highest order one. But yes. It's higher order than that one, but you're right, there's 3 or 4 of them. So there is no principal axis, I guess is the way to say it. All right, so we're going to align Z along the C2, okay, for the purposes of our character table discussion today. And I think that you'll see that makes a little bit of sense. All right, so now let me ask you, if you had to guess, how do you think the X, Y, and Z coordinate system transforms in TD? What does that even mean? Do you know what that means?
I mean, are you asking if it transforms, like if each one of like the X, Y, and Z transform together, like you can't distinguish them? Or if they are distinguishable, like.
So that's a good first question to ask. Are X, Y, and Z distinguishable? How many of you would say no? Right, the X, Y, and Z directions are, I mean, they're not unique, right? I've chosen this one, but I could have chosen it anywhere, and you just can't tell the difference between them. They're the same. And so that should tell you that X, Y, and Z being indistinguishable will transform together. So the degeneracy of the X, Y, Z coordinate system is 3. And so what's the Mulliken symbol of the irreducible representation? Right, because when I ask you, how does it transform in TD, I'm asking, what is the irreducible representation of its symmetry? What's the symmetry of XYZ coordinate, of an XYZ coordinate system in tetrahedral? Well, you know it's going to be threefold degenerate because X, Y, and Z are indistinguishable. And so it's going to be a T Mulliken symbol. Does that make sense? So let's just write out the TD character table here and get a look at it. Okay, so in TD, like in every character table, the first row is going to be the totally symmetric representation. So this is how a sphere would transform, for example. Always going to have that collection of ones at the top. Okay. So lots of irreducible representations here. Turns out X, Y, and Z go together down here. Let's see all of that. So X squared minus Y squared are part of and make up a doubly degenerate set. That's why they're written out with the parentheses down there. And then this T2 irreducible representation describes X, Y, Z, X, Z, Y, Z, and X, Y. Those both are a pair of triply degenerate sets that transform together. I'm going to try moving this up to you guys. Let me know if you can see it. Is that okay? Yeah.
What's the significance of the quadratic functions here? There are no d orbitals anymore.
Well, this is a character table, regardless of how you're using it. So it's true that in methane, we don't consider d orbitals, but you could. Or you might say, we're going to do titanium tetrahydride next, okay? And then you'd have to ask, how do the d orbitals transform? X, Y, Z, that coordinate system, you can also think about it as px, py, and pz. Right? So for methane, px, py, and pz are going to have T2 symmetry. All right. How about the 2s orbital? What's the irreducible representation that describes the 2s orbital on carbon? A1. A1. Always going to be A1 or AG or A, the top row. Sphere is the simplest. All right, now let's do something slightly different. So now we're not going to talk about the central atom, but let's talk about the 4 hydrogens. How do the 4 hydrogens transform? What's the symmetry of 4 hydrogens? We haven't done that yet. Okay. So there's a couple of ways to do this. What I want to know is what is 4 hydrogen 1s representation. So this is kind of like, remember we did vectors where we apply symmetry operations to vectors. That's what we're doing in this case. It's not a simple vector, however, it's 4 different, it has 4 components to it. And what we're asking is, what is the trace essentially of that matrix that describes the positions of the 4 hydrogens? One of the ways that you can figure that out is by putting a hydrogen 1s orbital on each of those positions, applying each of these operations, and then asking whether the atom moves. If it moves, it will send it off diagonal, and it will not contribute to the trace of the product. Forget about the matrix stuff for just a minute and just memorize this method. If you apply the matrix and the thing you're looking at moves, it will contribute a 0. If it doesn't move, it will contribute a 1 to this reducible representation. So for example, we have 4 hydrogen 1s orbitals here. If I do the do nothing operation, what is the value here? 4. None of them moved. And this makes sense because we're considering something with 4 components. The dimension of this thing is 4. Okay? All right, so now let's do a C3 operation. How many of them move? 3 of them. The one that's on the axis stays put. It spins, but it's a sphere, so it's unaffected. So this thing is going to be a 1. C2, 0. All of them move. S4, same story. Sigma D, 2. So this guy, the axis contains 1 hydrogen. Plane. 2 hydrogens. Okay. All right, so this thing now, if you look at this guy and then you say, all right, well, what's the symmetry? Well, there's no irreducible representation that matches this. In fact, this thing represents the trace of a matrix that can be broken into blocks. And the blocks are described up here. Okay. So which blocks can you use to describe this?
A1 plus 2, 2.
You take 2 of these things and add them together here. And William guessed A1 plus T2. You can just sort of by inspection estimate this might be the case. Aren't that many combinations really. Could be two E's, it could be A1 and T1 or A2 and T2 or whatever. So these are the irreducible representations that describe the hydrogen on the surface. Now, what's another way to have guessed? What I'm going to say is like a couple of lectures ahead, but you're going to do this probably in the future. It's the best way to solve these problems. One way is to ask yourself, which orbitals do the hydrogens and methane connect to on the carbon? Yes, two P's, right? So PX, PY, and PZ. You know they make a bond. So they're going to have the same symmetry. You can't make a bond if they don't have the same symmetry. So you might say, all right, well, I know what PX and PY and PZ are because I have this character table that tells me. I know what an s orbital function is. They have the same symmetry. This trick gets really handy when the molecules get more complicated. Symmetries aren't so high and stuff like that. All right, there's another way that you can figure this thing out if you get really kind of lost. There's an equation. So what you do is you take the character of the irreducible representation that you want to test out, multiply it by the character of the reducible representation that you're trying to decompose. This coefficient is the number of members in the class. So if you have 8 C3 operations, and then this is the order of the group. You add that up over all operations, and the product of that is the number of times that the irreducible appears. So this is kind of the magic of group theory. More detailed course would explain why this is the case. But it's a property of having all of the symmetry organized. I of R is the character of the reducible representation. Sorry, this is not quite right. Character of operation R. Reducible representation. And then C is the number of members in the class. So let's do. We're gonna do these 4 hydrogen 1s's. Their reducible representation. So you can search for whether or not there's an A1 or how many times an A1 appears here. We're going to multiply the character in the reducible by the character in the irreducible by the coefficient. So the character in the reducible is 4 times the character in the irreducible. A1 is easy, right? It's just a 1 every time. And the first operation is an E operation, which occurs once. And then there's the character in the reducible is 1. The character in the irreducible is 1. And now we're doing the C3 operation, which appears 8 times. Again, reducible and irreducible, now we're doing a 0. 1 times 3. Again, a 0. 1 times 6. And then a 2 times 1. 6. Okay. Multiply all that stuff out. We get 4 plus 8 is 12 plus 0 plus 12 is 24. Sorry, I forgot to multiply by the order of the group. The order of the group is 24. So 24 times 24 is equal to 1. And that tells you that A1 appears 1 time in this reducible representation. So if you wanted, you could just subtract A1 at this point from this 41002, and you'll see that you end up with T2. You could keep going. I think, I don't know. All right, so let's just stop for a minute and think about what we did. So we have 4 hydrogen 1s's at each of the corners of our cube, and we're asking, what's their symmetry like? What does that mean? It means what irreducible representations can be used to describe them. In the end, we arrived at irreducible representations A1 and T2. And what that says is that the 4 hydrogens can have a symmetry where it's spherically symmetric, sort of the same in all directions. Or they can have a symmetry that's T2-like. Well, what's T2 like? T2 like is like an XYZ coordinate system. Okay, what does that mean? Well, it's kind of like PX and PY and PZ symmetry. How do you get the hydrogen 1s's to look like PX and PY and PZ? We're going to draw that out here in just a second. But we're trying to figure out what the symmetry is. And group theory makes it really nice and easy. You do this trick. If they move, they contribute a 0. If they don't move, they contribute a 1. So we're doing 4 hydrogen 1s functions. When they don't move, all of them contribute a 1. This one's on the axis. One of them is on the axis. The other 3 are off. So when you do the operation, one of them doesn't move because it's skewered by the axis. It sits there. It contributes a 1. So you do this whole thing, you get your reducible, and then you figure out what the irreducibles are by inspection or by doing this trick with the equation. Or what was the other one I said you really need to know? Compare the symmetry of the orbitals of the central atom that you know are likely to make a bond. You know the p orbitals make a bond, the carbon p orbitals do. So probably it's going to have T2 symmetry because that's what the symmetry of the p orbitals are. Okay, so let's draw this stuff out a little bit. We're going to draw out what are called salps. Symmetry of that with linear combinations. We're going to do it for A1. So for our 4 hydrogen 1s orbitals here, and then I'm going to draw, best of my ability, this carbon 2s orbital. Okay. The question is, how do I shade them in? What I'm trying to do is to draw the bonding combination here. We're going to write out the bonding orbital. And the question is, how do you make a bond? Well, in this case, it's going to be a sigma type of interaction because there are no nodes involved in this s orbital whatsoever. And so the hydrogen 1s's must have the same symmetry as the orbital to which they're making a connection. Right? So everybody's going to have the same sign. Okay. So now this molecular orbital has A1 symmetry because both the s orbitals on the hydrogens and the s orbital on the carbon have A1 symmetry. Okay. This is the A1 irreducible representation for the hydrogen 1s's. Now there's also the antibond orbital. What does that look like? Okay. This is the antibonding orbital. Both the hydrogen 1s's on the orbitals on the corners have A1 symmetry. This carbon 2s orbital also has A1 symmetry, but they are out of phase. So these two components both have A1 symmetry, but now they're out of phase. They have a bonding and an anti-bonding combination. But the antibonding orbital, despite the fact that it's out of phase, still has A1 symmetry. If you were to take this orbital and apply all the symmetry operations to it, you would see that it has ones in all the columns. All right, so how about the T2 orbitals? T2 is the other one. It's a triply degenerate orbital. And it has the symmetry of the p orbitals, right? X, Y, Z. So let's write out the T2 type. Start with bonding. Got our 4 hydrogen 1s's. And remember, we've chosen our axis system like this. Each face of the cube is orthogonal to the X, Y, and Z direction. So let's put in a p orbital here on this carbon that's aligned with our coordinate system. Okay, because p orbitals are like the X, Y, Z. This thing here is going to be the PZ orbital. How do we make the 4 hydrogens with T2 symmetry? The thing to remember about these irreducible representations is that they have like a nodal structure that kind of defines them. MOs in general have like the symmetry has a nodal arrangement. You're asking about the shape of the wave. The wave is defined by where the nodes are, their orientation in space, and the number of them. So you have a PZ orbital here pointing along the z-axis with a node running through it. And that means the top half of this MO is the opposite sign as the bottom half. And so these hydrogen 1s orbitals are going to have the opposite sign as the ones on the bottom, because there's a node running through this cube, slicing the top and the half, slicing it in half. The top is going to be shaded, the bottom is unshaded. You can see by shading the hydrogens that way, you end up with a bonding interaction. Take this p orbital. Here. This is along the y direction. Let's shade this half. So again, we have a nodal plane that defines this p orbital that's cutting the cube left and right. The hydrogens on the right-hand side of the cube have the same shading as that little. Okay, so now those hydrogen 1s orbitals have the same symmetry as a px. And last but not least, the front and the back. So those bonding MOs are triply degenerate. They're the same in all directions. It's a combination of the px and py. Okay, so now I'm not going to draw the anti-bonding combinations, but what do they look like? Split the sign of one of the components, and then they're out of phase with each other. But they still have T2 symmetry, right? T2 symmetry is a description of the shape. So forget all the components for a second. T2 is where there's one nodal plane in the slicing z and minus z, and x and y are in that plane. You do that 3 different ways. Okay, that's the x, y, z coordinate system. That's how x and y and z transform in T2. It's saying the top half is 1, the bottom half is -1. Yeah.
So you're saying that the bonding and anti-bonding orbitals that correspond with each other always have the same symmetry?
Yes. Yeah. We're asking how you can make combinations of the component orbitals that we're mixing together in a way that obeys, or as described by the symmetry of the space. To make a bond, the atomic orbitals that you're combining must share symmetry. If they don't share the same symmetry, it's non-bonding. If they share the same symmetry, it could be bonding or it could be anti-bonding. Okay, so to get an MO, you have to have the same symmetry. Okay, so let's make the molecular orbital diagram now. So we're going to combine our carbon orbitals with our hydrogen orbitals. We have to consider the ionization energies, right? Position things on the page. So let's start off with our 2 p orbitals here, our 2s orbital there. These guys are at minus 19.5 electron volts and minus 10.7 electron volts. These are the energies relative to vacuum. You put an electron into one of these orbitals that was in vacuum, undisturbed in empty space, and you get out 10 electron volts. That's a lot of juice. Almost twice that to go into a 2s orbital. These are big differences in energy. Hydrogen 1s's, we have 4 of them. And this guy comes in at minus 13.6. Is the ionization energy of hydrogen 1s. So it's 6 EVs from the carbon 2s and 3 EVs from the carbon 2p. And it falls in the middle. Now, what is the symmetry of a 2s orbital in carbon and methane? Yeah, in the middle of our coordinate system, a sphere is always going to be A1. Two P's, well, you just go look up XYZ on your character table. This guy is T2. How about the 4 hydrogen 1s's? We just did that, all right? A1 plus T2. So now you can say, all right, well, I got an A1 down here, I got an A1 up there. I can make a bond because they have the same symmetry. T2 and T2, I can make a bond. There's the A1 interaction. And there's the T2. This molecular orbital down here is 1A1, and people typically use lowercase letters to indicate the symmetries of molecular orbitals. This here is 1 T2. This is 2A1. And this is 2 T2. Those are the symmetries of the molecular orbitals we're making. Now, then these are, what type of symmetry would you say these bonds are? Are these sigma, pi, delta? All of them are sigma. There's no internuclear nodal structure in these things. There are nodes here though, why aren't those pi? Because the hydrogens don't fall on the nodes. To be pi, they should share the same nodal plane, okay? Running along the bond. Delta, they should have two nodal planes that run along the bond. So this is a sigma bonding interaction. This guy is a sigma bonding interaction. This thing is sigma star. This thing is sigma star. All right, let's add some electrons to this. Okay, since we're starting with atoms, I'm going to put in 1, 2, 3, 4. I'm going to put in 1, 2, 3, 4. You could have started by putting 1 here and 3 there. That's fine too. I just want to count the number and make sure I have the total number correct. Okay. So let's then take these 8 electrons and put them into the diagram. This thing here is the HOMO, and this is the LUMO. Okay, so neat and tidy. There is the MO diagram for methane. Now, does this in any way bother? Is there something that looks surprising or unexpected about that diagram?
The 4 bonds, the 4 CH bonds are not degenerate.
Why do you say that?
Because each electron pair represents one bond, presumably, and one of them is in the K1, lower than the other two in T2.
Yeah, so I would say it slightly differently than what you said, okay? But what you said is basically correct. So the CH bonds in methane are identical, right? But the electrons that are in the bonding orbitals of methane are at different energies. How's that possible? This is a different kind of a picture, okay? It's true that all the CH bonds of methane are the same. But the molecular orbital structure is like this. And you can see that by doing spectroscopy. Okay. So let's take a look at the photoelectron spectrum of methane. What is that? You take methane and zap it with an X-ray. An X-ray is the sort of energy you need to ionize methane, to rip an electron out of its orbitals, which are quite low in energy, and send that electron out into space. The X-ray collides with the electron, wham, takes off. And when it leaves, generally it has some kinetic energies. The electron is accelerating through space. And if you can measure the energy of the electron, you can determine how deep the electron had to, how deep the well was that it had to escape from. Okay? So you take the energy of the X-ray, you take the energy of the photoelectron. And the energy of the photoelectron that's leaving, that is excess energy than what was required to get it out of the well. Minimum required amount is the ionization. So this is a pretty handy technique. You take your X-rays, you know the energy of the X-ray that you're using. You zap your substance, out come photoelectrons, you measure the kinetic energy. The difference is the well. All right, so if you do this experiment, you can see. Usually, what you do is you plot these energies versus some kind of intensity. This is the number of photoelectrons. Have some noise to it. You're going to get a bump. So this is the ionization energy down here. So what you're doing is you're actually scanning through, measuring the kinetic energy, and then you use a spreadsheet to change the results into ionization energy. This is a plot of the kinetic energies that are shown there minus the X-ray energy, and it gives you the ionization energy. Or the other way around, X-ray minus the photoelectron gives you the ionization. So the interesting thing about this plot here is that the area under this curve, and that curve is about 3 to 1. Okay. So the relative intensities of the two peaks is actually consistent with the degeneracies of the molecular orbital structure. Okay. So there are two different energies. Another way to think about this is think about the product, the CH4 radical cation that you make. There's two different positions that positive charge could be in. The carbon might say, well, you know, it's better for me if the plus charge is up and using p orbitals. And that, the way that I think about reconciling this issue, the CH bonds all being the same in the starting methane and getting two different energies, is that when you put the hole, the carbon will partition into orbitals, stabilize the hole most effectively.
So basically what we're seeing is like an after effect.
It's not an after effect. It is a measurement of the energy. It is the product that you form is different in those two cases where you put that hole. Okay. So, you know, the amount of energy it takes to produce the product where the hole is down in the A1 orbital versus in the T2 orbital is different.
When you say that the orbital is partitioned, does that change like the actual shape of the molecule, the symmetry of the loop?
Yeah, so in the photoelectron experiment, it's basically instantaneous. Okay, the X-ray comes in, blasts out the electron before methane knows what's going on. And then the product CH4 cation that you make will do other things. It might change shape, it might, you know, change bond length, I guess is a way to say it. It might also decay again, right? So if you ionize the thing, put the hole down there in the 1A1 level, well, methane can give off 9 electron volts by letting that electron drop. And so it will probably emit an X-ray. You ionize the A1 and then the product is so unstable, electron drops, out comes the new X-ray of 9 electron volts. Yeah.
So when we do this measurement, are we measuring a property of a CH4 or CH4 plus?
You cannot measure them separately. It's the difference between those two that defines the energy of the transition.
I guess I'm asking because you said that we see this because in CH4 plus, the orbital is partitioned. So then, in my mind, how I interpret that, or what it seems like to me, is that we're just measuring properties of CH4 plus. We don't really know what's going on with CH4.
You can't distinguish the two. So like, people often make this mistake when they're talking about an equilibrium energy. Or let's say a common thing in organic chemistry is to use a phosphorus reagent that is sort of primed to do some reaction. Usually, like, let's say it's a phosphorus 5 halogen compound. Those sorts of molecules will rip oxygen out of stuff to make a phosphine oxide. And it's often said the driving force for this reaction is the phosphine oxide formation. And they argue about how probable it is based on the halophosphine starting material and the phosphine oxide product. But you cannot dissociate. You have to also think about the other components in the equilibrium to define the energy of the transformation. So you can't easily rip an oxygen out of titanium dioxide paint. So it might not be downhill if you're ripping an oxide out of alumina or something like that. So you can't dissociate. The energy difference has to consider both sides of the arrow and all of the species involved. Inescapable. And a very important thing to remember when arguing about energies and equilibrium constants. Do you have another one? No?
So the 13 electron volts would refer to the partitioning of the p orbitals for the carbon, and the 22 electron volts would be if you were to rip it directly from the sigma bond, the A1 orbital.
Yeah, that's a way to say it, exactly. Right.
Because it's a deeper well.
Yeah, exactly. Yeah. So what you'll find is that these molecular orbital descriptions are really useful when talking about spectroscopy. Most of the time, spectroscopists use symmetry labels and MO theory, and organic chemists like to think about the bonds all being the same and hybridization, shapes, and stuff like that. They're kind of just different perspectives on the same thing.
So I have one more question.
Yeah.
I don't know if it's a good question or not, but like Hugo was saying, so the 1A has a deeper well, it's 22 electron volts to remove that electron.
Mhm.
And then say you apply 22 electron volts, you want that electron. You want to pull that specific electron. How do you avoid, since you're already more than 13 electron volts, how do you avoid pulling the other electron out instead?
Well, this is a question of probability and statistics, and the participants don't care what happens. There's a cost to remove an electron from that orbital and that orbital. There's a probability of removing one orbital versus another one. The intensity of the transitions tells you about the probability. It's 3 times more likely to ionize this T2 orbital and the A1 orbital when you have an X-ray of whatever energy.
Okay.
So it's just probabilities.
So when you say like 13 eV or 22 eV, that's the ionization energy to bring the electron back to that field, right?
Yeah.
Essentially. Okay, so that makes sense. Then my next question, I guess, would be if the T2 orbital has ionization 13 eV, that seems like it would be higher than the starting hydrogen orbital. Right?
It costs more energy to pull the electron out of the bonding orbital than it is out of the hydrogen. 1s, yeah. Because electrons are stabilized when making the bond.
Well, so if the ionization energy is 13 eV, then the T2 bonding orbital would be minus 13, right? Which would be higher.
That's correct. So maybe there's something wrong with my labels.
Is the 13 literature known or something?
Well, these are all very well known numbers. So I need to check. Maybe I've gotten something wrong here. You would expect it to be somewhere around 19, based on how my diagram is wrong anyway. I'll have to go look into that. Thank you. Okay, now let's keep going because
If there's more than one electron in the orbital, though, does that change the ionization? The
no.
first and second electron have the same ionization.
The first and second have different.
Yeah, but for example, hydrogen, right? Even though they're both in 1s, they have different ionization energy.
Yeah, because in one case you're making a 2+.
Yeah,
in which case you're making a 1 plus.
so that's probably what's going on, no, because if you have 6 electrons at the first, only the last electron is gonna be the energy of the orbital, right?
No, I think that I think Ethan's point is correct, that there must be some kind of a mistake here. The energy of that T2 is gonna be a couple electron volts lower than 100.
But all 3 will have the same ionization energy, that's what I don't understand.
Well, there's, the T2 level is triply degenerate. This is the first ionization energy. But there are 6 electrons that could come out.
Oh, but it's the first ion.
It's the first ionization. The second would be pulling a second electron out of the T2. Now you're making a 2 plus or 1 plus. That's gonna be bounding more tightly. Okay, so let's do the same sort of a compound, this time titanium instead of carbon. All right, so let's do titanium tetrahydride. The solution here is going to be about the same for titanium tetramethyl. Okay, it's about the same. And so we're going to do molecular orbital diagrams for a bunch of different compounds. And we're often going to treat the ligand orbitals around the metal. The ligand orbitals are going to be treated kind of like hydrogen 1s levels. Okay, if you were doing this for titanium tetramethyl, you could choose, let's say, an sp3 hybrid as your basis set. We're going to treat sp3 hybrids of these ligands around this metal as being like the hydrogen 1s orbitals on titanium tetrahydride. Okay? We can pick our orbital basis however we want. We could pick the orbital basis as 2s and 3 2p's if we wanted to, and it would make the diagram a lot more complicated and less useful to us. We'll make it more complicated later in a way that is helpful for understanding the compound. For now, you can imagine a CH3 and a hydrogen as being very similar. So let's determine the irreducible representations for the various parts. And first of all, titanium 3D. What is the reducible representation for titanium 3D? Look it up on the table. The table tells you, right? What does the table say this is going to be? X squared minus y squared and z squared are E, xz, yz, and xy are T2. How about titanium 4P? We already did the p orbital symmetry. Let's do that. How about titanium 4S? Opposite one. So you're asked, what is the reducible representation of the orbitals on titanium? You should say T2 plus A1. Okay. We've already done the gamma hydrogen 4s. So let's write out this diagram. Now we're taking we have our T2 symmetry for p orbitals. We have our A1 symmetry for S. Have our 3Ds, which are T2 plus. Where do the hydrogens go in this diagram? Lower. Okay. Hydrogens, and in general, the ligands are going to be lower. Okay, there are a few exceptions to that we're going to talk later, but in general, the ligands are gonna be lower. This is not always true, but for this class, we're gonna treat it as being true. Okay? It's gonna make things approximately right most of the time. I'm gonna draw them down here, 1, 2, 3, 4, hydrogen one acids, the other T. A1. So I'm gonna make an A1 connection here. Sorry, I'm kind of running out of space. 1, 2, 3 for T2. But notice there's also a T2 up here. Things get a little complicated now. We have T2 symmetry, p orbitals, d orbitals, and s orbitals. So I'm going to draw this bond down there first. And there's going to be some kind of an anti-bond. And this, I'm going to draw a line here. Here. Like that. That got a little complicated. These T2s and these T2s all have the same symmetry. When you make linear combinations of the orbitals, you can combine P's, D's, and hydrogen 1s's to make MOs. Because these have the same symmetry, you can make linear combinations of all these components to make an MO. All right, now, we forgot about the E. Who does the E make a bond with? Nobody. So we can't forget about it though. It's got to end up in our diagram. We're going to have an E set floating at the same energy as the starting d orbital. Right? So we got a 1 T2 here. We have a 1 A1 there. We have a 1 E orbital there. This is of T2 symmetry. This is of T2s. And this is of A1s. There's 3 different MOs of T2 symmetry. And how many electrons do we have? You're going to have to figure out how many valence electrons the transition metals have to do this, which means you need to know your table. Titanium has 4. The hydrogens have 4. 4 hydrogens, 4 titaniums, 1, 2, 3, 4 bisons. So the bonding orbitals down there have the 8 electrons in them. These orbitals up here are empty. These are empty. In transition metal compounds, we are generally interested in these ones right here. Okay. Titanium tetrahydride, they're empty. In many other transition metal compounds, they'll be filled. The reason we're interested in these is that they are comprised of the d orbitals. They have some p orbital character, but we talk about them really as being like the d orbitals. In other symmetries, the p's and the d's won't have the same symmetry. And you'll see there are 5 orbitals here that we get excited about. We spend a lot of time talking about it. We're going to call these guys here the frontier orbitals. These are the orbitals where the action happens. The reactivity, often the color, the magnetism comes from Okay, so. Think of my time. Let me just say one thing. 4S and 4P are on this diagram above 3D. In transition metal compounds, we're going to include these orbitals. Okay? We talk about the 18 electron rule in transition metal compounds, the 8 electron rule. In order to have an 18 electron rule in a transition metal, you need these orbitals. They are relevant to the bonding of transition. 4P is higher than 4S, which is higher than 3D. Same is true for the heavier orbitals. The last thing is those hydrogens are below the metal. Okay, you got to do that. If you don't do that, this is an important thing to remember. You don't start with your ligands below your metal, you're in trouble. So we're going to come back to this diagram next time. And I know it's 10:20, it's time to go, but I'll just do a few questions if you want to pack up and leave. It's cool.
So why is the 3D lower in energy if it fills after? Why does the 4S fill before the 3D?
Yeah, okay, so in the atomic electron configurations, you'll find titanium is like 4s1, 3d3 or something like that. It's 4s2, 3d2. In transition metal complexes, where there are ligands and the metal is kind of ionized, that is no longer true. Okay, and so we're going to order it this way: 4p, 4s, 3d, and forget about the atomic configurations. The atomic configurations are actually kind of all over the place. We're not going to think about that. We're just going to do 4p, 4s above 3d. This energy ordering is the one you should always use. It is not consistent with the electron configuration of the free atoms in the gas phase. You have another one? Okay. All right. Thanks, guys. We'll see you next time.
Okay, see y'all there. See y'all there.
Yeah. Will your brother?